This video is going to give a quick overview on what equilibrium is, how it works, a few examples, and then it's going to look at 2 example questions for dealing with equilibrium constants and how to calculate the equilibrium constants from given concentrations, or how to find the concentrations to then work out the equilibrium constant. So when we're talking about equilibrium, what we're talking about is a reaction that is reversible. And so if it's reversible, it will usually have this double arrow, but it's not really a double arrow. What it is, it's an arrow showing that the reaction can go forward as well as backwards. So for example, you could have written A plus B goes into C plus D, and what this reversible arrow tells us is that actually we have the reaction A plus B that produces C plus D occurring. And then once enough of C and D is made, C and D can then react to go the other way to produce A and B again. So C plus D could also create A plus B. In order to save on time, therefore we use this reversible arrow to show that, okay, for this whole entire reaction of A plus B going to CD, it can also go backwards. However, this will only work in a closed system. And that's because if the system is not closed, meaning in some sort of reaction container or vessel that wouldn't allow any mass to escape, if mass was to escape, you might lose some of your D or your C, and therefore it wouldn't be able to do that backward reaction. So when we're looking at equilibrium, we're not looking at, okay, how fast are we making our products here. It's about how much of those products are being made, and that gives us an idea of, okay, is this reaction, the forward reaction, producing more, or is the backward reaction producing more? So if we're looking at what the Kc value is, Kc, what we're doing is we're saying, okay, how does the concentration of the products compare to the concentration of the reactants? And if we have a high amount of products, so this is large, compared to a small amount of reactants, then if a large number divided by a small number is going to give you a number greater than 1, so greater than 1, which means that, okay, we've got more of A plus B going to C plus D being produced. Alternatively to this, if this number is small and now our reactance is large, a small number divided by a large number is going to give you a Kc that is less than 1, meaning that, okay, actually the reaction of C plus D to A plus B is going to be favoured. Now, as we said before, this was our forward reaction, and this one was our backward. And so that gives us an idea of whether we're going to get a lot of the products or more of the reactants produced. And we want to know this because then we can kind of manipulate it for different situations. We're not going to look at manipulating it today. All we're looking at is calculating the equilibrium constant based on concentrations, or finding the concentrations to calculate that. So for example, let's have a look at just a generic version of an equilibrium constant expression. So iodine can break down into iodide ions, so it's a reversible reaction. It can become I- quite easily, but in order to balance that out, we need a 2 in front, and these tend to be gases. And so because it's a reversible reaction, we can either have I2 forming I-, or that I- then going back and turning into I2. So if we were to write an equilibrium constant expression for that, though, remember we put our products over the reactants. Now, in this case, we've only got one product, which is the I-, and we've only got one reactant, which is the I2. But when we're writing these equations, it's actually very important to look at our coefficients. So because we have coefficients, they play a role in our equilibrium expression, and they go up the top. Now, because there's no number there, we assume 1, and so really you can just leave the 1 off. But this would be the equilibrium constant for a reaction of I2 to iodide ions. And when we have that reaction occurring, let's just say we got a Kc value of 5.6 times 10 to the negative 12. Now this value here is less than 1, and so that tells us that actually we're probably not going to get a lot of this I- produced, and so it's going to favor the backward reaction. And so that's what that number means, or that's how that number comes into it. So it tells us whether we're going to get more or less of our products, and so therefore which reaction's being favoured. So let's look at another example question. So what I'm going to do is I'm going to put this example up, I'm going to read the question out, and then have a go. So pause the video, have a go at doing the question, and then I'm going to go through the working out for it. So in this practice question we have phosphorus pentachloride, which decomposes to phosphorus trichloride and chlorine gas via this reaction here. It is a reversible reaction as indicated by our reversible arrow. And for this example question, 1.10 moles per litre sample of PCl5, so reactant here, was placed into a vessel. At equilibrium, the concentration of PCl5 was determined to be 0.33 moles per litre. Now the question is, calculate the Kc for this reaction. So remember, we have to work out our equilibrium expression for this, but the idea is that equilibrium constant expression, that Kc, that has to deal with the concentration of the products and reactants at equilibrium. Now at the moment we've only got information for the PCl5 at equilibrium, so we're going to have to work out the concentration of the others at equilibrium first, and we do that using the ice method. So first of all, you have a go at working out the concentration of these two at equilibrium, and therefore what the equilibrium constant number will be, and then continue the video to see the working out. So a very common way of doing that is the ICE method. So ICE stands for initial, change, and then equilibrium. Another way I like to show this when I'm working out is I say I see that delta for change, and then I use the shorthand that for equilibrium. And the idea is we want to know for each of our reactants and products what their concentrations were initially and at equilibrium to work out our expression. Now, because I haven't left myself a lot of space, I'm going to put the different reactants and products down the bottom. And so that's for the PCl5, PCl3, Cl2. Now at this point we're not worrying too much about the coefficients, although looking at this, each of the coefficients is just one. But what we do first is we put in the information that we know. So we know that initially we had 1.10 moles per litre sample of PCl5. So initially this was 1.10. Initially, if just this was placed into the vessel, we can assume the vessel was empty unless they tell us otherwise, so there would have been 0 amounts of products. And then at equilibrium, the concentration was 0.33. Now we don't know what the other two are, but we have this information. And what we do now is we have a look at our reaction equation and say, okay, what were the coefficients? Because the idea is that you're going to need 1 mole of this will decompose to create 1 mole of this and 1 mole of this. So our mole ratios are very important as well. Now, if we've got 1 mole of this turning into 1 mole of that, 1 mole of that, we can say that this the change in PCl5 is going to be X. So we're going to lose X or minus X, and we're going to gain 1 lot of X for each of these because of our mole ratio of 1 to 1. Now, if we know that we started off at 1.10, we minused a number and got 0.33, we can work out what that X is, and that gives us an idea then of how much this PCl3 and the Cl2 should have gained. So let's just first do working out X. And so our X is going to be 1.10 minus 0.33, which is 0.77. And so that means that if I lost 0.77 here, I had to gain 0.77 lot here, and we had to gain 0.77 lot here. And so because I started off at 0, I can say that, okay, this is going to be 0.77, this is going to be 0.77, and so now I have my concentrations and equilibrium. So we're going to put that into our equilibrium constant expression, which we haven't written yet, but that's all right. So remember, we put our products on top divided by reactants, and the products are going to be times together. So it's going to be PCl3. Now, because there's no coefficients except 1, we just assume that's 1 up there, and we times it by Cl2 divided by PCl5. And so because we know the concentrations, we're going to substitute those numbers in where applicable. And so that's going to be 0.77 times by 0.77 divided by 0.33, which gives us 0.01797. So this number is less than 1, so that is less than 1, meaning that the backward reaction is a lot more favored for this reaction. So that was one example of working out the concentration of the products and the reactants, and then working out the Kc expression. Let's look at another one. So same deal here. Have a look at the I'm going to go through the question and then pause the video and have a go yourself. So in this one, we've got a colourless N2O4 gas decomposes to a brown coloured NO2 gas via the following reaction. Now this one's a little bit different because now we have a coefficient other than 1 in front, so our mole ratio is going to be a bit different, so we'll see how that changes our working out. And this question says a 0.125 mole sample of N2O4 is introduced into a 1.25 litre container and allowed to decompose. At equilibrium, the number of moles of N2O4 is found to be 0.0750 moles. What is the Kc value for this reaction? And are the reactants or products favoured? So pause the video, have a go, and then have a look at the working out. Okay, so this question is a little bit different to the other one because in this situation we're working with moles instead of concentrations. So what we're going to do is first we're going to convert these number of moles into concentration because we know that the container vessel is 1.25 litres, and we're going to work out the Kc value that way. However, I will show another method that also works without converting it to concentration first, but let's just do it the normal way first. So we're going to use our ice method for this. So initially we had a certain concentration of N2O4, so because we were given it into moles first, I'm going to convert that into a concentration. So it's going to be 0.125 divided by 125 litres. That is 0.1 moles per litre. And then, so 0.1 moles per litre. And then at equilibrium, it was 0.0750. So concentration of that is going to be 0.070 divided by 1.25. So that is 0.06. So 0.06. Now, initially we had a 0 concentration of NO2. Now, if we look at our mole ratios, it's a 1:2 ratio. That means for every 1 lot of N2O4, we're going to create 2 lots of NO2. So this is going to minus X, but this is going to go plus 2X. Now, we don't know what this is, but we do know the change from N2O4, so we can work out what X is from there. And the idea is that X is going to be the difference between it, so 0.1 and 0.06, which gives us 0.04. And so since X is 0.04, and over here for our NO2 we're going to go plus 2X, this one here must be 0.08 instead, because 2 lots of that. So now we know the concentration of N2O4 and NO2 at equilibrium. So now we can do our equilibrium constant calculation. So our equilibrium expression, just to start off with, is going to be NO2 to the power of 2 divided by the concentration of N2O4. And so that's going to be 0.08 squared divided by 0.06, and that gives us 0.1067 altogether. And so this Kc is less than 1, so again the reactants tend to be favoured. However, the way I've done it, I calculated the concentrations first and then worked out the Kc expression from that. However, when we do our ice method, we don't necessarily have to do it with concentrations. We can also do it using the number of moles. So the idea is that if you do it with moles, you are going to get slightly different numbers for the different things at equilibrium. However, you still need to change it into a concentration for this, and so then the ratio between them should work out in the end. So if we were to do it with moles instead, our ice method, so initially we had 0.125 and 0 moles, and then we had 0.0750 moles there. Now we're still saying minus X and plus 2X. So here it's just going to be that X is a little bit different. So X is going to be 0.125 minus 0.075, which is 0.05 altogether. And so then 2X will be 0.10. And so now we know the number of moles at equilibrium. We convert these to a concentration. And so because the vessel was, 1.25 litres, the concentration is going to be 0.06, and the concentration of the other one is going to be 0.08, which is the same as what we got up here. So what we've done is we've done it a slightly different way, but we've still ended up with the same values for our Kc expression. So it doesn't matter if you do the ice method with concentration or doing it with moles first. The benefit of doing it this first way is that because you've already converted it to concentration, you don't need to remember to change it for the Kc expression, whereas if you do it with moles, you must remember to change it to concentration first. Otherwise you'll get the wrong answer. But this is a completely legitimate way of doing it as well. So often you might be asked to do it only with the information of moles given first, and then in maybe the next step you're told the volume for that. So those are two examples of how to work it out, or using the ICE method to help you with doing questions when you need to calculate the equilibrium constant. If you found this useful, give it a like, and stay tuned for the next video.